let's talk about some of these words. What is a force? Anyone other than Travis, what's a force?
A push or a pull.
A push or a pull, love it. Something that tries to make something move. I can apply a force and have no resulting motion. I'm applying a force to the wall, it's not moving. I can apply a push and have nothing change, but force is the goal usually when you're applying a force is to make something move. Gravity tries to pull us down. We won't get into relativity. Okay. Suppose I have concurrent forces. Suppose I have some object here. I'm pulling this way with 10 newtons of force. We use newtons to measure force. And I pull this way with 10 newtons of force. What's going to happen to that object? Come on, mate.
It's not going to move.
It's not going to move. We say it is in static equilibrium. It's not moving. This is essentially Newton's first law. Newton's first law says, Newton's first law says basically, now you don't need to know the laws as quotes. In physics you do, especially in maths you don't, you need to understand how to apply it. But basically it says, if forces are balanced, we'll talk a bit more about that in 2 dimensions in a minute. If forces are balanced, no acceleration. If forces are unbalanced, I can't even spell, balanced, then you will have non-zero acceleration. Well, I may as well write the whole word out. Travis, you remember a good quote of Newton's first law as proper words? Something like a body in equilibrium, a body experiencing no net force, no, how do you say it? A body will continue in linear motion at a constant speed unless acted upon by a net external force, something like that.
Yeah, that's actually pretty accurate.
So, I taught physics for many years, so basically, if the forces are balanced, it's not that it's not going to move necessarily. It could be moving at a constant speed, it just won't change. It won't change speed. If the forces are unbalanced, then there's going to be some acceleration. How much acceleration comes from Newton's second law? I want to talk a bit more about this first. What happens if I go... Oh, no, maybe I should just do second law. Already do that. Newton's second law says the acceleration is the force divided by the mass. That is not the way you usually see that written. I write it the same way when I do physics. You would be probably used to seeing that from year 10 physics as F equals ma. But the force is not a result, is not calculated from the mass and the acceleration. No, the force is applied and it results in an acceleration. That's why I write it that way. The force is applied, it's divided by the inertial mass and results in an acceleration. The more mass you have, the less acceleration you're going to get for the same force applied. If I push like this on a chair, it's going to accelerate. If I push like that on a car, it might not move at all, or if it does, it might accelerate very, very slowly. Bigger mass means less resulting acceleration for a given force. So suppose in one dimension again I have, let's call this, make our numbers nice, let's go a 3 kilogram mass, this way with 10 newtons and this way with 20 newtons. what's going to happen to my mass? It's going to accelerate left, correct. By how much? Well, the net force is 10 newtons left. Maybe I'll write the word towards the left. So the acceleration is going to be 10 over 3 meters per second squared to the left. And if you always use meters and seconds and newtons, you'll always be right. And kilograms, you'll always be right. Okay. Of course, it might not always be like that. How much room am I going to need? Probably more later. What happens if I have... too big. What happens if I have my 3 kilogram mass and I pull this way with 10 newtons and this way with 20 newtons? Roughly, approximately, which way is it going to go? Travis knows. Come on, year 11s. Roughly which way is this object going to be accelerating?
That way.
That way, correct. We can be precise. Redraw this to go, we've got 10 newtons this way, 20 this way. The object is going to be effectively accelerated by a force in that direction. That is my net force. I need to know the size of that force and the direction. Let's go like this and go, that's north. The size of my force is the square root of 10 squared plus 20 squared. I didn't choose nice numbers. You're going to need a calculator.
Do you want a third?
Good question. Yeah, give me a third.
10 square root 5.
10 root 5 newtons. That's approximately, give me a decimal as well, so we have a vague idea.
22.36.
And it will depend on context whether you think you need a decimal or an exact. I also want to know this angle. Opposite on adjacent. That I'm going to have to give you an approximate. Paradoxically, even though we love radians, directions are usually given in degrees. But you can give me either.
Should I change my thing to degrees, right?
Yes, or you can just get your answer and times it by 180 on pi. Whichever you prefer.
63.43.
That'll do degrees. So I'm going to write my answer as net force. Oops, that was an S. Net force is, let's go approximately, 22.36 newtons, and I'm going in direction east, 63.4 degrees south. Come up with some other way of describing this if you don't like east something south or north something west. Just make sure you give the direction. Too easy so far for you. Yep. There could be three forces acting. And you would just do the same thing. Do I need to show you a 3 force acting one? I've got some not at right angles in here. Sometimes the question might ask you to say what is the additional force you would do to make it not accelerate. Well, in this case, I would want this much force in the exact opposite direction to bring it into equilibrium. So if I wanted to apply a third force to this object to make it stay still or not accelerate, I need to apply 22.36 newtons west, 63 degrees north in order to make it not accelerate. You might have situations where I won't do it, but I'll show you the picture. You might have something that is resting on a surface, and you might be pulling it like this. Maybe I will do this, but give me an example to talk about another thing as well, friction. Suppose I'm on a surface that has some friction. Friction always opposes motion. Always, always. I might even write that. Friction always opposes motion. Always opposes. So if I'm pulling it this way at an angle of 30 degrees with 25 newtons, and there's a friction force of 4 newtons, the friction force always pulls directly backwards because it opposes the direction it's going to move. And let's give this thing a mass. I'm not using the one in the textbook at all, am I? I can just make something up then. Let's go 4 kilograms, because I seem to like 4 this morning. What's the resulting acceleration of this box? So that's 30 degrees to the horizontal. I'll let you draw the diagram. Sorry, Travis, year 11s are not used to drawing these diagrams yet. You can just try the exercise if you want to. You don't have to wait for us. I think you already are you?
I'm just...
Yeah, having a go. Yep. This force on the string that I'm pulling it along with pulls it up a bit as well as across a bit. But the upwards force is going to be cancelled out by the gravity. So I can ignore the up bit, I only need to know what the across bit is. I only need to find out this part of that force. The horizontal component of my force here is going to be 25 cos 30 to get this length. 25 cos 30. And cos 30, if you want an exact value, is... Anybody? Travis, remember?
Pi on 6.
Okay, what's the cos value?
Square root 3 on 2.
Root 3 on 2. You don't need to get to that point where you know it. 25 root 3 on 2. Or, you know, I probably want approximate. 12.5 times 1.7, I'm not going to do that in my head, something around 20.
21.65.
21.65 newtons. So effectively I'm pulling it forward with about 21, 22 newtons. Friction is pulling back with 4 newtons. What's the net force acting on that object? it's this minus that. I'm going to do it here. Net force 21.65 minus 4, 17.65 newtons. And so I think am I going to fit it here? If I put it here, Claire can't read it, huh?
That's fine.
If I write another 2 lines?
Yeah.
Okay, and the acceleration is the force divided by the mass. 6.5 divided by 4. Oopsie. Approximately 4.3?
4.4.
4.4 meters per second per second.
And you said we're not doing pulleys, are we?
We're not doing pulleys, we're not doing connected bodies, correct. It's ambiguous in this one, but they said the new syllabus clarifies what their original intention was. The year 11 will be very happy about that until they get to it in physics next year. They're doing physics. So, force, resultant force, now action and reaction. Newton's first law, Newton's second law, Newton's third law. How do I phrase this properly? Did I actually talk about it here as Newton's third law? Probably not. It's action and reaction, but how do I... Maybe I'll just say that. If I apply a force to the wall applies exactly the same force to me. Exactly the same every time, all the time. If I'm applying force to something, it's applying the same force back to me. The Earth is pulling me downwards. I am also, at the same time, pulling the Earth upwards. But my mass is much smaller, so my acceleration is much higher. The Earth's mass is very big, so for the same force, it barely moves. But the same force is acting. In particular, if my book is resting on the desk, maybe I'll do that where the camera can see it. If I put something on the desk, or hold it up, the book pushes down on my hand due to gravity. My hand pushes back up on the book with exactly the same force. We call this force pushing back up the reaction force. Or sometimes you might hear it called the normal force or the normal reaction force. Let me draw you a picture. Surface, object on the surface. I really like my 4 kilograms at the moment. If I say what forces are acting on that object right now, well, gravity is pulling it down now. Force, in this case, is the weight force. I know my acceleration due to gravity is 9.8, little g. So my force must be my mass times that. Weight force is mass times g. 4 times 9.8. .6, 39, 38.2, 39.2.
39.2.
Yeah. Because gravity's pulling down at that, but it's not actually accelerating, there must be another force acting. It's not accelerating down towards the Earth. So this surface must be pushing the object back up. at exactly the same amount. I tend to write R, it's the normal reaction force. That was messy. Why is it called normal? It's not because it's ordinary, it's because it's at right angles to the surface. The reaction force is always at normal to the surface, at right angles to the surface. On a flat surface, that's easy. This reaction force here must be the same amount. It has to be. But what if I put it on a slope? Now what forces are acting? I'm not going too fast, year 11s, you're keeping up. Gravity is still acting on this mass, vertically downwards. We already knew that, mg, 39.2 newtons. But the reaction force is now perpendicular to the slope, always at right angles to the slope. That's my reaction force. How do I work out how much reaction force there is? You have a choice. Travis might remember this from physics. I don't know how Mr. Lee teaches it. You have a choice. You can either work up and down, or you can work along the slope and perpendicular to the slope. It is usually easier to work along the slope rather than up and down, because the motion of this body is going to be down the slope or whatever. So it's normally easy to work this way, like this way rather than that way. So what we're going to do is turn this weight force into some amount perpendicular and some amount parallel. And if we add them as vectors like we did over here, we can work this out. What is this angle here? What is this angle here? How do I work out what that angle is? A little bit of geometry for you. Anyone want to have a go? This angle is 90 degrees, right? So if this is 30, what's this one up here? What is it, Shannon? What does this one have to be?
60.
Correct. If that one's 60 degrees, then what's this one have to be? Because that's also a right angle. 30 degrees. This angle is the same as that angle, always. So what we do is, I'll draw you a general one. If that's theta, I've got my weight force down. This one is mg, that's theta. So this is mg cos theta, and this one is mg sine theta. And you will sometimes see this written as weight force perpendicular, and this one is weight force parallel. That was messy. I'll see if I can neaten that up a bit. I'm going to write it horizontal first as well. That's theta. This is weight perpendicular, mg cos theta. And this one here is weight parallel, mg sine theta. So you have a choice. You can draw the diagram and work it out every time, or you can use these two formulas. So this one here is going to be 39.2 cos 30 degrees. Just give me an approximate decimal answer. And this one is going to be 39, this one was this one, to sine 30 degrees. That one's half. That's 19.6 newtons exactly. This one's going to be around 30 newtons. What is it actually? Is Rain the only one working his calculator this morning?
Seems to be. Do you want a third?
No, I give you a decimal.
33.95.
Oh, almost 34 newtons. 9.5 newtons. We'll into a couple more questions. What was the amount of the reaction force? Well, no other forces are acting into or out of the plane, so my reaction force must equal my weight force perpendicular, i.e. 33.95 newtons. See, the gravity's pulling down, but not all of that down actually goes into the surface, so the surface doesn't push back with quite as much as the full weight. You okay, Claire? So what happens then to the rest of the force? What happens to this bit of the gravity force? What happens to this box on the slope? What's going to happen? A force is pulling it this direction, a little bit of force pulling this way. What's going to happen to the box? Come on, you 11s. I put an object. If I put an object on a sloping surface, what's going to happen? It slides off, right? Don't think I broke it. It should be right. If the question says the surface is smooth or frictionless or whatever, then this is going to be the only force that's acting. If they don't say that, they give you a friction force, well, friction is going to be holding it upwards and you have to calculate a net force. In this case, let's say it's smooth, then my net force is going to be 19.6 newtons down the slope. So my acceleration is going to be 19.6 divided by 4, 9.8, 4.9, 4.9 metres per second down the slope. I'm kind of going over my other picture here. Should give myself more room. Does that refresh you on inclined planes, Travis?
Mm-hmm.
Okay, good. So if it's smooth, there's no other force. If it's got friction, you might have to think about which way friction is pulling. Friction always goes the opposite direction to the motion. So, friction is actually a bit funny. I don't know if you ever tried to push something really heavy that doesn't have wheels on it. And you initially have to push really hard, but once you get it moving, it's easier to keep it going. Friction is like that. There's a limiting friction or a static friction that opposes starting motion. But once you get going, there's a sliding friction that's actually smaller. Imagine this box on the slope. If I just put it there, there'll be friction pulling it back up the slope if it wants to slide down the slope. If this force down is smaller than my limiting static friction, it won't actually move at all. On the other hand, I might have a string attached pulling it back up the slope. If I'm trying to pull it this way, which way is friction acting? Back down the slope. So you might have to go my tension in my rope versus the weight force down and a separate friction force. Work out the net force, then the acceleration. So just be careful about which direction friction's actually acting. It's always going opposite to motion. Now I don't know how much this exercise does. Just having a quick look. Most of this is uniform. I think it is. Oh no, until the very end. I have said acceleration is force divided by mass. All of our forces so far, all the net forces have been constant forces, which results in constant acceleration. But there's no reason this has to be constant. The simplest example, I throw something up and let it come down again. On the way up, air resistance acts down. On the way down, air resistance acts up. Do it in two pieces. But if on the other hand, I'm going to move this. If on the other hand I might have, let me see. Oh, I really do need a bit more ink in that one. If on the other hand I have an object on a slope like this, I'm going to start with a strong accelerating force this way from the weight. But by the time I get to the bottom, I've got very little accelerating force and most of the weight is now turning into reaction force. So my force is not going to be constant on the way down. What does that mean? It means acceleration is not constant. You just get the force, whatever the formula is, divided by the mass. And then you're using calculus to work out where it's going, how long it takes, all that stuff we just did. Make sense? Acceleration might not be constant because force might not be constant. I am going to leave, because I don't think this talks about it yet. Wait, no it doesn't. And I'm going to have to find you some more questions about momentum. So I'm going to leave momentum for the moment. I think you have enough. Exercise 8.3. You can ignore connected bodies, two things joined to each other. You can ignore any questions that have, how do I do this? Something on a slope, something hanging off the end with a pulley, anything complicated with multiple things joined together, you are allowed to ignore. There are a few questions like that in there. Oh, one more thing to ignore. You will always get the friction here, motion of a body. It doesn't even particularly mention friction. In particular, you can calculate friction as some coefficient times the reaction force. This coefficient depends on the two surfaces. One might be paper and the other wood or whatever. You don't have to know about this in specialists. In fact, you don't have to know about it in physics either. It's not in the syllabus. Both this book and the physics textbook talk about it. But you can ignore those questions that ask you to work with this. If you want to just work out the total friction as a constant number once with this, with the coefficient they tell you, and then just use that friction force only. This is not in the syllabus. They will always just give you a amount for the friction or a formula for the friction. Have a go. That's a problem solving.